Hey, everybody. I did, yes. The repairman came, he fixed it. It was just, the valve just wasn't screwed on well, so, it's good. Never, usually not a good thing when you go to do your laundry and you smell gas coming out from the dryer. So, we got that fixed and yeah, good thing too. Yeah, I'm almost out of underwear, so it'd be good to do, yeah, to be able to do laundry. Let's see.
Hey, Professor, I have a quick question.
Yeah, what's up?
So I was doing the homework for number problem. For problem, if I remember well, was it was QE. I mean, I have a question on that too, but I was calculating my answers for problem three A.
Yeah.
And I put the matrix into MATLAB and everything.
Yeah.
And for some reason, when I calculated for my deformation,
Yeah.
I just got the forces. I just got the force of 95 kilonewtons and negative 95 kilonewtons. And I was
Okay.
wondering, or if you could, or if you had like any idea of to why that might be.
When you compute your deformations, you get 95. You get 95,000 and minus 95,000.
Yeah, I get the forces that are supposed to be acting on it, not the deformation. Because I use the backslash.
I think it'd be easier if you want to send me your MATLAB code so I can take a look, and then I think that'd be easier for me to see.
Okay, thank you so much.
Yep. Hello. Oh yeah? Yeah, I've heard some good things about the God of War game too. Yeah. Yeah, the rain was insane. My dryer chose a good day to to act up because I don't want to drive to campus on a day like today. I don't know, Samsung dryers got my back. He predicted the weather because we smelled gas over the weekend, and then we called the repairman yesterday and said he can only come out today. So yeah, Samsung dryers cannot predict the weather. Maybe just a lucky break. Okay, it's 5:30. Let's go ahead and get started. So first of all, I want to say thank you everyone for being flexible today. Maybe it worked out just because it's super rainy and cold today, and so maybe not that many people come to campus anyway. But thank you guys for meeting on Zoom today. My dryer got fixed up. It's all good now. Repairman came, he fixed it up. It was just the valve was just not screwed on well, and so he fixed it. So I should be back on Thursday. Which is good because we actually have an ANSYS activity planned for Thursday, and so it's definitely good for me to be there for that. Okay, all right, and so this week we're going to be pivoting back to ANSYS, and so we spent a few weeks talking about the direct stiffness method, and so that's kind of the theoretical side of finite elements. And so I think we've done enough to have a midterm exam about, and so of course that midterm exam is going to be next week. But starting from now until the end of class, we're going to be working just on ANSYS stuff. Okay, so of course you guys are working on your final projects, and so I know you guys are thinking about that. But we're going to do a couple more activities on some of the more, I would say, specialized parts of ANSYS. And so this week we're going to do something. I think this is probably one of the coolest activities. We're going to learn about dynamics analysis. Okay, and so these are analyses that can change with time. And we're going to use that on Thursday to do a finite element simulation of a car crash. And so, that's going to be really cool. So, hope you guys can look forward to that. And then after Thanksgiving, we're going to learn how to do modal analysis, which is how you can compute things like natural frequencies, resonance, using FEA. Just because I think that's in the past, that's been something that's been requested and something that's useful for a lot of the student projects that you guys work on. And so so you guys can look forward to that. And so I think next next week I know is going to be pretty hectic just because it's first falls before Thanksgiving and we have the midterm exam. But once the midterm exam's done, we're going to focus just on ANSYS stuff. Okay. All right. And so I think that's all my announcements. Oh, I graded your midterm project. So I finished grading your midterm projects on Friday. And so if you look on Canvas, you should be able to see your scores. And so, of course, you can see your scores in the gradebook, but if you go to the actual assignment itself, I left a comment on everyone's assignment with an attached rubric. And so if you want to see how you did on each of the sections, you'll see on the rubric. And for a lot of you, I've left a lot of comments in the rubric itself. And so, please read the rubric, because, the final project, the rubric's going to be very similar. And so in the areas that you might have missed some points, you can definitely read the rubric there. And so, you can make up those points on the final, or at least you just not make the same mistakes on the final exam, on the final project. Okay. All right. And of course, if you have questions about, if you have questions about why I took off certain points in certain areas, or you want to kind of discuss your midterm project, definitely let me know. I'm always open to discuss those things. And so you can either come to office hours, you can send me an email, any of those things, and I'd be happy to explain further, why I chose to kind of give scores the way I did. Okay. Okay, and so that's, I think, everything that I had to say. You guys got so I sent out the study guide for the midterm exam yesterday. So make sure you please are using that study guide. You use the study guide as well as the problem set that you're working on right now. And so if you kind of study those two things really well, I would say, you'd be in really good shape for the midterm exam. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. All right. And so, like I mentioned at the beginning of class today, how long is the midterm? It's going to take up the whole class, and so it's going to be all 75 minutes. And so right now I'm planning 2 short answer questions, and so 2 kind of conceptual questions, and then 3 problem solving questions. So 3 questions where, I'm going to give you kind of an assembly of truss, spring, beam elements, 1D, 2D, and then you're going to have to go through the finite element process. And so element stiffness matrices, assembly, and boundary conditions. Yes. Okay. Yeah. Let's talk about the logistics for the midterm exam. So the midterm exam is going to be in class on next Thursday, and so you have to show up in person, and so there's no plans to offer it virtually. And so please, show up to class on that Thursday. And what you can bring for the midterm exam is you can bring your writing utensil. And so it's going to be on 11/17, so that's next Thursday. Okay. And so the things you should bring: writing utensil. Okay. Pencil, pen, I don't really care, whatever you feel most comfortable with. Calculator. Okay. Scientific graphing calculator, whatever is lucky for you. I had a lucky calculator for like 12 years of my life. It's actually right here, but it's kind of not been doing well. It's like literally, I think almost like 17 years old now. And so, I've been trying to fix it, but it's kind of on its last legs. Okay. So writing utensil, calculator, and a cheat sheet. And so your cheat sheet is an 8.5 by 11. 8.5 by 11 sheet of notes. You can use both sides. And you can write it or you can type it, whichever you feel kind of most comfortable with. Okay. All right. So the only requirement that I have for the cheat sheet is that you be able to read it, which sounds silly, but I don't want people to bring a magnifying glass into the midterm exam. And so you should be able to read it, without kind of going like this to the cheat sheet. But also at the same time, if you try to squeeze too much information onto the cheat sheet, I've seen people try to just take just take screenshots from all the notes and just put it on like really small print on the cheat sheet. That's also, not really helpful, because you're going to spend more time looking through the cheat sheet, trying to find the information that you need, than actually doing the exam. And so I think what I see often is that for people that do that, they leave 60% of the exam incomplete, because they spend so long trying to look for the answers for something else, rather than kind of trusting themselves and just kind of just doing their best from there. Okay. And so there's a balance. And so, of course you want to have as much information on the cheat sheet as possible, but you don't want to waste time on the exam looking for stuff because I will say that for this particular exam, because there is a lot of writing involved with the element stiffness matrices and all that stuff, it is going to be a little bit time constrained, and so you don't want to kind of waste too much time kind of like looking at hunting through your cheat sheet rather than taking the exam. Yeah. Okay. All right, so that's information on the midterm exam. We can talk about it more if you have questions on the format and everything. We can talk about it at a later time. Okay. All right, and so let's get into the topic for today, which is transient finite element simulations. Okay. And so when I say transient, basically a transient situation is one that changes with time. Okay. And so if you'll notice one thing about all the answers that we've done, basically all the finite elements that we've done, they've all been static situations. And so they don't actually change with time. But finite elements is not just limited to those situations. So you can actually use finite elements to do unsteady situations as well. Okay. And there's a lot of good reasons to do so. And so there are a lot of engineering situations which are going to move. Okay. And before, we didn't really have a way to analyze those, but with kind of the tools that we're going to learn on Thursday, we can do it. Okay. All right, question. So Jade, yes, yeah. So that's basically, so if you look at the chat on Zoom, that's basically the format for the midterm exam. So there's going to be two short answer problems where I ask you kind of conceptual questions about the direct stiffness method. And so those you can answer in 2 to 3 sentences. And then there's 3 kind of free response, or I call them problem solving type questions, which are very similar to what you're working on in the homeworks. And so, yeah. And so that's basically the format that I have in mind for the exam. Yeah. Okay. And so, that's the situation that we're going to be looking at this week. And so I will say that, the world of unsteady simulations in general, not just FEA, is very, very vast. And so, this is one thing where, we're going to learn the absolute basics. And so, I think ANSYS kind of does enough to let you kind of get started with it and to kind of get something done. But if you really want to learn more about it, all the nuances, the intricacies, the theory, and how to set up, more sophisticated situations, you're going to have to go kind of way beyond this class. And so we're spending just a week on it. But, I will tell you that, I've spent, probably 3 or 4 graduate level classes learning about kind of the intricacies of doing unsteady simulations. And so it goes deep, but, there's enough that we can do in a week to learn the basics. Okay. But I think, one of the strengths of ANSYS and part of what makes it so popular is that it makes situations like this very user-friendly. But at the same time, with ANSYS, especially with dynamic simulations, ANSYS kind of does a lot of things for you. And so you're kind of pushing buttons and, you're kind of setting things, and you may or may not understand kind of what you're really doing. And so, it's good for some basic results, but, like I said, if you really wanted to do this professionally, there's kind of a lot more that you need to learn to kind of augment what we're doing in class. But, the reason I'm doing this, and so, a lot of beginner FEA courses that you'll see, they don't really dive into dynamic simulations or transients, just because, a lot of instructors kind of feel that it's too much to cover. And I understand that, but I think it's also good to, I also want you guys to be aware of kind of what you can do in ANSYS, and to at least get your feet wet in some of these tools, so that you can kind of use that as kind of a launching point for learning more and for studying more. Okay, and so that's kind of my motivation here. And so it's just gonna be 1 week. Of course it's towards the end of the semester, so we've kind of gone through all the meat and potatoes of this course already. And so the reason I bring this in, first of all, it's really cool. I think it's awesome, but I want you guys to kind of be exposed to it and to know that it's out there, so that you can kind of use it to learn more. Okay, so that's kind of my motivation. And so I want to make that really clear that there is a lot more to learn about dynamics. Some of it will be related to what you've probably learned already in some of your other courses, but there is a lot more that you can learn. Okay, all right, any questions on this so far? Okay. All right, so let's start with kind of what I consider to be one of the simplest dynamic models out there. Probably it's one that you've seen before, either maybe in like a math class, or maybe in a vibrations class. But there's actually a lot of good insights that we can pick up from this that can apply to how we simulate these quantities, and it's what I call the lump mass model. Okay, and so the lump mass model is nothing more than just a damped mass spring system. Okay. Okay. So it looks something like this. Okay. And so if we attach to the wall, and we have let's say we have a spring, and so the spring constant has or the spring has a constant K. On the bottom side here, we're gonna have a dash pot. Okay. And then to this, we're gonna have like a mass here. Okay, so it's like a block of something. It has a mass M. And then we're gonna be pulling on this with the force F. Okay. And then we're going to say that it's going to displace in that X direction. Okay, and so if you pull on this on the system, and you let it go, then it's going to vibrate. Okay. Okay. And of course, one key assumption that I'm making in this case is that the system is underdamped. And so, if you kind of remember that term from 308, or maybe your vibrations class, all that really means that the damping that we have in the system is not that great. And so when you have kind of a spring system like this, and it's underdamped, and you kind of, you stretch it and you let it go, it's going to basically vibrate in place, because the spring is going to be constantly applying like a restoring force. Okay. Okay, and so for a mass spring damper system like this, we can form its governing equation, which involves derivatives in time. Okay. Okay, so the governing equation is we have mass times the acceleration, and so the acceleration is d squared x dt squared, okay, plus c dx dt. So that's the damping term, plus kx. And this is equal to f. Okay. And so probably what you've done in a previous class is you've taken this differential equation and you've solved it. And so it's nothing more than just a second order ordinary differential equation. And so you can solve this for the time evolution of displacement which is the displacement as a function of time. Okay. Okay. All right. So even though this is a fairly simple system, it's also kind of a fairy tale system, I call it, because you almost never see a mass attached to a spring and a dash pot. That never happens in real life. But this simple system and this simple equation we can actually extrapolate to a lot of different physical situations to learn more about their behavior. Okay. And so first thing you might be noticing is that this equation right here is a differential equation, right? And so there's derivatives, and so you might be thinking, hey, it's a differential equation, and so we're in a finite element class, and so what we know about differential equations is that we can solve this with FEA, right? Okay. Right, so that's coming from this class, that might be the first thing that you try, right? And so I think we haven't actually done it in this class. We haven't taken a differential equation and broken apart with FEA. That's more of kind of a graduate level thing. But I've been kind of hammering it into your guys' head this whole semester that FEA is a way to solve differential equations. And so you would think that a differential equation like this, we could solve it with FEA. Well, the reason I'm kind of being a little bit dodgy is that you can't, this is kind of a special one, in that you can't actually solve it with FEA, okay? The main reason for that is time, okay? Okay, and so when your differential equation involves time, you actually can't solve that directly with FEA, at least not the FEA that we, that we've been using. Okay. And we'll talk more about it, a bit later. But basically, the upshot is that time is a causal system, and so the way time works, that time works sequentially, right? And so, in order for you to know what's going to happen, in the next second, you have to know what's happening now, okay? And you can't really do that out of order, and so you can't really solve for something in the future and then kind of back solve for something in the past, right? That's not really how time works. And when you solve for things with FEA, where you kind of create this giant kind of linear system, if you notice in direct stiffness, right? And so we created we formed our element stiffness matrices, we formed our global stiffness, we applied our boundary conditions, and we solved it. We kind of solved for every node's solution kind of at the same time. And so it's kind of a simultaneous solution technique. And so, you have kind of a collection of nodes in space, and you can solve for all those things at the same time. Time doesn't work like that. And so, you can't take like the whole spectrum of your entire life and kind of know and solve for everything and predict everything that's going to happen, all at once, right? And so you kind of have to go through your life kind of sequentially, right? And so that's kind of the main reason why we can't solve with FEA. Okay. And so there's a different class of methods that we actually use to solve these time-dependent problems, and those are called time marching schemes, and we'll get to that in a bit. Okay. But first, let me go ahead and draw what the solution looks like to you here, because that's going to be kind of a key to how we view a lot of these dynamic solutions. Okay. And so for this particular case, for this particular simple ODE, we can actually solve this by hand because it is a 1D ordinary differential equation. Okay. And so it looks like this for an underdamped system. And so we have x of t is equal to a e to the minus bt times sine omega t plus b. Okay. The exact exact form of this is not that important, but what is important is the graph of the solution, which is kind of what we can observe in ANSYS. Okay. And so if we were to graph the solution, it would look something like this. And so we'd have oscillations, but generally those oscillations will go down with time. Okay. And so this solution here, even though it's very simple, I think is very kind of emblematic for the way a lot of physical objects respond to dynamic stimulation. Okay, and so generally speaking, if you kind of strike a system, if you kind of excite it, and you kind of let it kind of go on its own, you're going to observe some vibrations. Okay. Okay, and so if you look at kind of the dynamic response, or if you look at kind of the how a system is kind of responding in time, what you're going to notice a lot of times is these kinds of vibrations. And so this simple mass spring damper model, even though it has just 3 constants, this is able to pick up that vibration kind of behavior. And so kind of before the age of computers, this simple kind of mass spring system was used a lot to design, huge buildings even. So very complex stuff. And how this is actually used comes down to the parameters itself. So, the spring constant, the damping constant, and the mass, how you choose those three things and how they affect the dynamic response is kind of key to understanding dynamics. Okay. All right. Any questions on this? Okay. Okay, so let's take a look at those 3 parameters, because understanding those 3 parameters is kind of key to this whole operation. Okay. All right. So let's look at the mass first. And so for the mass, okay, mass is generally the easiest of the 3 parameters to measure. And so if you look at kind of a complex structure, finding the mass is fairly simple. And so, on the one hand, you can just weigh it. But even if you can't weigh it, you probably know what the material composition is. And so you can get the density and to get the mass. Okay, so mass, easy to measure. And generally speaking, the more mass that you have, the higher the amount of inertia you're going to have. Okay. And the more inertia that you have, the harder it is for that object to kind of change its motion, right? And so if you remember Newton's first law, I think it's his first law, it said objects in motion tend to stay in motion. And that's kind of the law of inertia. Okay. And so what this has to do with vibrations is that the more inertia that you have, the smaller the lower the frequency of vibrations it's going to be. Okay. Okay. And that makes sense. And so if you have kind of a really massive object, it's going to vibrate a lot slower than kind of a smaller, lighter object because it's just so much more massive. Okay. All right, next we have the spring constant. And so, I know we've been talking about springs a lot in direct stiffness, but this is kind of just a general kind of spring constant. Okay. And so, of course, most objects in the real world are not actually springs, but the spring constant still provides us like a good analogy for us to make, because a spring constant tells us approximately how stiff the material is. Okay. Okay. And so generally speaking, if your material property is more stiff, or in other words, it has a higher Young's modulus, its effective spring constant is going to go up. Okay. Okay. And so generally speaking, the stiffer your material is, or the higher your spring constant is, that's going to increase the vibration frequency. Okay. Right. And so, I mentioned with the mass, the mass is fairly easy to measure. The spring constant is not as easy to measure because, it depends a lot on the material composition of the object, but it also depends on its geometry, right? And so if you think back to our direct stiffness method, when we looked at truss elements, it's entries in the element stiffness matrix dependent on, its Young's modulus, of course, but it also dependent on its areas and length too. Okay. And so, this was a little bit harder to measure for kind of a general object, but that's something that a lot of scientists did back then. A lot of engineers did, before they could run FEA simulations. Okay. All right, and of course, the last one here is the damping. And so I gave that the symbol C for the dash plot. Okay. And so the higher the damping, the better your system can suppress the vibrations. Okay. Okay. And so damping, out of the three, damping is probably the most difficult to measure because it depends on a lot of kind of factors that are difficult to measure. And so a lot of times the damping is, usually either, specified by experience or by empirical measurements, but, it's not something that you can just kind of look up in a system. Okay. All right. And so the reason I'm kind of bringing this up, and the reason I'm kind of talking about this kind of mass spring damper, is that, understanding this system is important for understanding the intuition behind dynamic situations. Okay. And so to kind of give you some context, before the age of computers, the way scientists and the way engineers kind of design things dynamically is they kind of drew comparisons to this mass spring damper. And so, let's say that they're designing a car, right? And they want to kind of design the car to be kind of stable, and they want the car to be, safe in dynamic situations. And so what they did was that, they weren't able to solve, complex partial differential equations, because they didn't have the technology back then. But what they did was they used a system like this, and they said that, okay, for our car here, we know its mass, okay, because we can weigh it. We have a general idea of its stiffness or its spring constant because we know what materials are going into it. And then for the damping constant, we have a lot of kind of mechanical tests that we've done to tell us, what kind of damping there is in our car system. Okay, and then just based on those kind of very simple pieces of information, they were able to use kind of an equation like this, solve it by hand, and then able to predict, a lot of the vibration behavior that their cars will experience. And so, even though it's a very simple system, this is kind of, the first, probably this is the first dynamic system that most people learn in school. There's a lot of comparisons that you can make with it, all depending on how you specify and how you set these kind of constants here. Okay. And so the reason I'm bringing this up is that, when we're kind of getting into dynamic simulations in FEA, it's important to kind of remember this system here so that you can also kind of draw the comparisons. And so when you're kind of observing your results, or you're kind of debugging your results, just know that your dynamic simulation is also going to depend on the mass of your system. It's going to depend on the spring constant of your system. It's going to depend on the damping in the system in exactly the same way. And so, you may not be able to specify it as directly as this one, but you'll know that, if you change the material to something stiffer, that's going to increase the vibration frequency of your response. Okay. If you increase the mass of your system, that's going to decrease the frequency of your response. Okay. Because a lot of dynamic simulations kind of boil down to vibrations. And so it's important to kind of, have a good grasp of the fundamentals just so that you can interpret your results. Okay. All right. Any questions on this? Yeah. And certainly there was definitely a lot of trial and errors back then as well. Mm-hmm. Okay. All right. So with that said, let's jump into how we actually find numerical solutions to these dynamic problems. Okay. All right, so like I mentioned before, when you have a dynamic problem and you have a differential equation that is dependent on time, we can't use our classical methods to solve these because FEA is not designed for causal systems like that. Okay, and so the class of methods that you use to solve unsteady problems is called time marching schemes. Okay. And so the theory of time marching schemes is very, very vast, and there's a lot to learn about time marching schemes, and there's literally hundreds and hundreds of them out there, and so there's a lot to go. And so, there's a wealth of information that you can find about time marching. We're not even going to get into some of the theory behind it, but if you are interested, there is a course next semester which I will likely teach because I've taught it 3 times now, which is EGME 417. And so we get a bit into time marching schemes there. So if you're interested, you can take that class, but you can also just learn some of the basics here. Okay. One really important thing that you need to know about time marching is that they are very, very resource intensive. Oh, I don't know what days it's offered. It's on the schedule, and so I'm not sure what days it's offered. Yeah. And so one thing you should know about time marching is that they're much more resource intensive than just straight up FEA. Okay. I should say compared to static FEA. Right. And so, probably your guys' impression of an expensive FEA simulation is something that takes probably like 5 or 10 minutes or 15, 20 minutes. But it's not uncommon for a time marching problem to take hours, maybe sometimes even over a day, compared depending on how intensive it is. And so the kind of the time scales that you need for time marching schemes is very, very different. And actually, I've seen some very sophisticated simulations take literally weeks to complete on some of the best supercomputers in the world. And so it's not uncommon. And so unsteady problems are kind of tough to do. Okay. And the reason for this is, I think, very quite simple to understand, at least from an intuitive point of view. Because when you're solving a static problem, there's really only one configuration that you have to solve for, right? So you apply all your loads, and the result of that is just a single snapshot, basically, right? Okay. Whereas dynamic results, you run a dynamic simulation, dynamic simulation is something that changes with time. And so of course, your result is going to change with time as well. And so what you're going to get from a dynamic simulation is not just a snapshot, but you're going to get like a video of results. Okay. Okay. And so one way that you can make a video is you can compute all the different frames of motion, or all the different frames of the of the motion, and then kind of splice them together. Okay. And so just very naively, let's say that you're creating a 30 FPS video. Okay. And so to get just 1 second of dynamic response, you have to solve kind of 30 frames or 30 snapshots in order to get there. Right. And so that's already like 30 times the cost, and it's actually more than that, because the time marching itself takes some cost as well. And so you're talking about orders of magnitude more expensive for dynamic simulations. Okay, so that's kind of another reason why this isn't taught very often in kind of introductory FEA courses, is because they are so time intensive. Okay. All right, so generally the way that time marching schemes work is that they seek to solve the solution at the next time. We call it the next time step, using the solution at the current time step. Okay. Okay. And so it looks kind of something like this. And so we say that u at n+1, where u at n+1, this is the solution in the next frame or the next time step. Okay. This is equal to some function. So f here is just some function of un, where un here, this is the solution at the current time step. So this is kind of our present reality. Okay. And also all of the material constants of the structure. And so, we have the mass of the structure, we have the spring constant of the structure, we have the damping, and we have other stuff as well. So all this stuff here is this is kind of the material properties of the system itself. Okay. All right, and so another kind of visual representation of this would be kind of in a timeline approach. Okay. Where each node or each dot in this timeline represents a frame at a different point in time. Okay. And so in order to solve for the next frame, so the n+1 frame, we go from n to n+1. Okay. And then to solve for the frame at n+2, we need the solution at n+1, and so that's going to give us n+2. Okay. And so this is the reason they're called time marching schemes, because you kind of march kind of one step at a time. And so just like I mentioned before, you can't solve for multiple time steps at the same time. You can only solve, one time step at a time. Okay. Okay. And you can actually see this kind of visually happening within ANSYS as well, which I think is actually a really cool feature. And so you'll see on Thursday that when you launch a dynamic simulation, what you'll see is that your solution will kind of start building up kind of time step by time step. And so you'll see the car impact, and then as the computation continues, then the car will kind of get scrunched up, and each time the image kind of updates, that's ANSYS kind of solving for the solution at the next time step. And so you'll actually kind of see this happening in real time, which is pretty cool. Okay. All right. Any questions on this? Okay. All right. So let's highlight kind of some important parts of this process. So now that we kind of understand how time stepping is going to work, there are some important parameters that are going to influence this process. And so the first parameter, probably the most important one, is called the time step size. Okay. And so the time step size is defined as the amount of time in between each of the different time steps. Okay. And so this delta t here that's defined as our time step size. And so basically what the time step size is, it's the amount of time in between the frames. Okay. So this is really important because if you know kind of a little bit how videos work, a lot of videos are rated by how many frames per second that they can show, right? And so generally speaking, the higher frames per second, that means that the smoother the video is going to be. Okay. And so the same is going to apply for our dynamic simulations as well. And so the lower your time step size, kind of the higher FPS or the higher frames per second that you're going to do. Okay. Okay. And so the time step size kind of behaves very similarly to the mesh size. And so, what do we know about the mesh size? And so the smaller that you make your mesh size, the more elements that you're going to have. And so you're going to have a more accurate, the more elements you generally have, the more accurate your simulation is going to be at the cost of, well, cost. And so the same thing is going to happen with the time step size too. And so the smaller you make your time step size, the smoother your video is going to be, the smoother your results are going to be, at the cost of more computation time, more computation memory. Okay. Okay. And so it's going to increase the cost of your simulation. Okay. All right. And so just like the mesh size. So when you do an unsteady simulation, you're going to have to mesh your simulation as well. And so meshing is not something that you can skip in dynamics simulation. But in addition to the mesh size, you also have to specify the time step size as well. Okay. All right, question. So will there be some kind of restriction for the student version? Actually, no. And so there's actually no restriction for the time step size for the student version. And so you can make it as small as you want. It's just that you're going to kind of sit there. And the reason for that is that you can make the time step size as small as you want. What's interesting about unsteady simulations is that it doesn't increase. The smaller you make your time step size, it's going to take you longer and longer to run your simulation, of course. But it actually doesn't dramatically increase the memory requirements. And so the thing with meshing, and it's a little bit hard to get into it kind of without kind of diving too deep into it. But the thing with meshing is that if you make the smaller and smaller you make your element size, you need a lot more computer memory to kind of store your mesh, okay? Because you kind of have to store the entire thing at once. But for unsteady simulations, you don't actually have to store all of the simulation results, at every time step at once. And so, the memory requirements do go up, but not dramatically. And so I think that's the reason why they don't really put a limit on how small you can make your time step size, as long as it's reasonable. And so as long as it's within the ballpark of a few milliseconds, then that's usually fine. But if you go to like 1 × 10⁻12 seconds, then maybe they might stop you. But I've never reached a limit with the student version. Right. Yeah, yeah, for this one too. And so I know the activity 4 I think was a little bit tough on your guys' computers. Activity 5 is probably going to be, this is probably the most computationally intensive activity there is that we're going to do this semester, because activity 4 I think was the second most, and activity 5 is definitely the most computationally expensive. And so if you can finish kind of all of the simulations on Thursday, then that would kind of benefit you a lot, because then you wouldn't have to run it on your own personal computer. Yeah. Okay. And so, if the time step size is something that you have to specify, you might be asking, how do you specify this, or what are kind of some rules that you can use to specify the time step size? And unfortunately, just like the mesh size, there is no kind of hard rule in terms of what you can specify. One thing you can do, just like you do with the mesh size, is you can do a convergence test. And so you can run your simulation at different time step sizes. And you can see, when your simulation kind of stops changing with respect to the time step size. That's one way that you can do it. It's not the smartest way because dynamic simulations take so long. To do a convergence test with, with time step size would take you probably, weeks or months to do that. And so, not a smart thing to do. And so a lot of times the time step size is kind of chosen, with some intuition. And so it's not really kind of done like the mesh size. And so the rule of thumb that I generally use for the time step size is that you should set it to be small enough so that you can reasonably capture all the phenomenon that you're interested in. Okay. And so that's very vague. And so, for example, one criteria that you can use is that if you do expect to have some kind of vibration or some kind of frequency response in your system, you should set your time step size small enough that you can capture all of those vibrations. Okay. And so, let's say that, as an example, you expect the vibration to be in the vibration frequency to be on the order of F. Okay. Okay. Then your time step size, delta T, for instance, would be 1/20 times F. And so this basically makes sure that you capture all of those frequencies. Okay. Okay. Right. And so in addition to the time step size, and so this of course is going to be different depending on the phenomenon that you're going to be looking at. And so for our case, for activity 5, we're going to be looking at an impact scenario. And so basically, two objects colliding at a very high speeds. And so the difficult thing with impacts is that a lot of this stuff happens very, very quickly. Okay. Not now, cat, go away. And so what you'll see, what you'll see in our activity on Thursday is that we're going to set the time step size to actually be very, very small. Okay. Okay. And so actually, compared to a lot of the other dynamic situations that I've done, actually the activity 5 on Thursday is going to be a very, very small time step size. And actually, I think we're actually going to let ANSYS kind of choose it smartly. But it's something to kind of keep in mind. Okay. Right. And so kind of the upshot of this is that what you set for the time step size, it just has to be small enough to capture all of your behavior. Okay. And so think about it, don't think too hard about it. And so think about, if you have a dynamic situation going on, let's say that, you're throwing a ball from one end of the room to the other one. And so your time step size should be small enough so that you can capture that motion pretty well. Okay. That's all it is basically. Okay. If you really want to get into it, there is a lot of very intense theory in terms of, how you can determine the time step size. But we're not going to go into that. Okay. The intuitive way to describe it is it should just be small enough to capture all of your stuff. Okay. All right. And any questions on this? I'm watching my cat chew on wires on the other side of the room. We'll finish up soon. And so after we finish up, I'll bring the cat so she can say hi to everybody. Okay. And so besides the time step size, the other main parameter that you have to set in a dynamic simulation is something called the end time. Okay. Okay. And so the end time is basically when you want the simulation to stop, simulating stuff. Okay. And so, if you have a timeline here, okay, well, all we've specified so far is kind of the space in between the nodes in the timeline, right? Okay. And so the space between this is the time step size delta t. Okay. But we also need to know when the simulation is going to finish simulating as well. Okay. And so this is t is equal to 0. Okay. This is t is equal to big T. Okay. And so the end time is basically what this time is over here. Okay. All right. And so for the end time, just like the time step size, you want to make sure that you specify the end time to make sure you capture all of the important behavior of your system. Okay. Okay. And so you don't want your simulation to be like one of those videos that ends too soon. Okay. All right. So as an example, let's say that you are simulating something that's going to oscillate and it's going to take 0.75 seconds to complete a full oscillation. And so usually when you have some kind of oscillatory behavior, you don't want to just capture just one oscillation cycle. Usually you want to do a few. And so you want to make sure that you set your end time so that you capture, at least maybe 3 or 4 oscillations, so that you kind of get a good sense of their behavior. Okay. And of course, everything, all of these descriptions that I'm giving you here for the time step size and the end time, these are, very, I would say called intuitive kind of descriptions. And so, there's when you're kind of first starting out, it is hard to determine, what are good values for these. And so unfortunately, experience is going to be kind of your best teacher for these ones, in terms of, specifying these variables. Without kind of diving too much into the theory. And so kind of as you run more and more of these dynamic simulations, as you learn more and more about the theory, you'll kind of get a better sense of, how to set these variables. Okay. And at least for me too, I know that, when I was first learning about dynamic simulations, I was working on a very specific application. And so for my case, I kind of first started learning these when I was doing blood flow simulations for my, for my graduate research. And so for those situations, I had kind of a wealth of experience that I could draw on. I could ask other people how they ran their simulations, and generally there was kind of a ballpark of time step size that I could draw from. And so, usually it's going to be something like that. But and so this explanation here for the time step size and the end time, it is very hand wavy. I know it's nothing concrete, but again, what I wanted to kind of teach you guys is kind of the general intuition and the general kind of logic that you follow for these ones. Okay. Okay. All right. Any questions on this? Okay. All right. So last thing I wanted to cover today is I just wanted to briefly mention the different tools that you have available in ANSYS for unsteady simulations. Okay. And there's two main ones, and so they're and it's not immediately clear what's the difference between them, and so I want to make sure we talk about it. Okay. Okay. And so the two types of unsteady tools that you'll see in ANSYS, one is called transient structural, and another one's called explicit dynamics. And so when you look at those two, it may seem like they're both similar, and they are. And so in some cases, it doesn't really matter which one that you pick, you're going to get the same results. But there are some kind of important kind of nuances between them that's important to know, so that there's certain situations where transient structural will work better, and there's certain situations where explicit dynamics will work better. Okay. All right. And so the exact differences between the two is one uses what's called an implicit method, and the other one uses an explicit time marching scheme. Okay. And so transient structural uses an implicit time marching, where explicit here uses an explicit time marching. Okay. And so, there's a lot of differences between these two, but I'm just going to talk about just kind of their general differences. And so for implicit time marching, generally these methods are a lot more stable. Okay. And so what that means is that it's less likely to kind of get away from you, because what can happen sometimes in unsteady simulations is that the simulation, kind of informally we say the simulation blows up. But what that means is that when you run the simulation, you end up with extremely high values that are not realistic at all, right? And so that's kind of a risk that you run with explicit time marching, is that if you don't set the time set size small enough, you might end up with kind of exploding values. But that doesn't really happen with implicit. So implicit kind of has a lot of extra guards in place to make sure that you are more stable. But that also means that those extra steps that you do are going to be a lot more costly. Okay. Okay. And so on a per time step basis, so each time step that you do with an implicit scheme, each of those time steps are going to be a lot more expensive. Okay, but they are going to be more stable and a lot of times more accurate too. But there are ways kind of around that too. Okay, and so the explicit time marching is going to be less stable, and so it's going to be more prone to divergence. Okay, that's kind of the official word that we call it. Okay. And so it's less stable, but you kind of get some benefit from that. And so you kind of trade some stability, but on a per time step basis, the computational cost is going to be lower. Okay. Okay. All right, and so what this means basically is that for an explicit time marching scheme, in order to make sure that your simulation is going to be stable, one way that you do that is that you can lower the time step size. And so for explicit time marching, it places a lot more restrictions, and you have to have a much lower time step size to get an accurate and stable solution. Okay. Okay. Whereas for the transient structural, which is an implicit scheme, you have kind of a bit more freedom, and so you can make your time step size a little bit. You can make it larger. Okay. Okay. All right. And so what does all this mean in terms of how you actually use these? And so when is one good and when is the other one good? Okay. And so for explicit dynamics, because you're so restricted on the time step size, you need a much lower one. This is really good for simulation or situations that happen really, really quickly that you want to use a small time step size for anyway. Okay. Okay. Because like I mentioned before, if you have a situation that's going to happen very quickly, you want to make sure your time step size is small enough to capture all that behavior. Okay. And so one great example of this that we're going to see on Thursday is a car crash or some kind of impact situation. Okay. And so whenever you have two objects kind of impacting each other, the impact and the damage happens very, very quickly. And so in order to kind of properly capture this, you're going to want to use a small time step size anyway. And so in those situations, you might as well use an explicit scheme because you're going to be using a small time step size, and so you won't have to worry about stability, and you want those small time steps to have less computational cost. Okay. On the other hand, there are also dynamic situations that you want to simulate that occur over a long period of time, right? And so maybe you want to see kind of the small development of some kind of deformation in response to load. And so in those cases, you don't want to simulate a bajillion time steps, and so you want to use larger time step sizes for that. And so for those cases, it's better to use a transient structural, which is an implicit time scheme. Okay. Okay. And so for situations where your end time is going to be in the ballpark of 5 seconds, 10 seconds, 20 seconds, that doesn't seem like a lot of time, but for simulations, it takes a long time to simulate those things. You're probably going to want to go with an implicit time scheme. Okay. And also, this isn't really relevant for for this class because we're using ANSYS, we're using a specific tool. But from a programming perspective, then it's actually a lot easier to program explicit time marching as well. And so usually, when you're first kind of starting out, you're first learning about time marching, then you kind of start by programming the explicit dynamics, explicit scheme, and then you kind of move on to implicit from there because that's generally easier to do. Okay. All right. All right. Any final questions on this? Okay, all right. So that's all we got for today. My cat ran away, so I'll try to go find it. I'll try to go find her again. But I'll be back on Thursday, and on Thursday we'll do activity 5. Right. So thank you everyone for coming today. Thank you guys for your understanding and patience for the virtual stuff. And hope you have a great day. See you Thursday. There, I found my cat. Here. She's hungry. It's almost her dinner time. Ow, ow, don't eat my arm. Ow. It's one of the nice perks. Before in COVID, when I would always teach from home, my cat would always make an appearance, almost always make an appearance in the class and stuff. Yeah. One thing I miss about teaching from home is get to spend all day with my cat. Ow, hey, don't scratch my leg. All right, question: if you want to work with someone for the final project, do we email you first? Yes, please. And so yeah, if you do want to work with someone on the final project, send me an email. Let me know what you guys have in mind. And then we can chat from there. Bring her to school. No, no, I think that's a little bit too much for a cat. She already freaks out whenever we put her in the carrier.
Professor.
Oh, sorry. Let me turn on my volume.
Yeah.
Yeah, what's up, Ozzy?
It's actually Jerry. I'm using his computer right now. I apologize.
Yep.
I have a question about biomechanics. It's really fast. On number 3, for part A, on your, I think it's on your moment equation. Your solution has 2 y components, but one has cosine and one has sine. I think that might have been an error. Let me see.
Let me see. So 3. I know that there is a mistake in the solutions for the dynamics one, because I didn't take the moments about the center of mass, and so I do need to correct that, and I'm probably going to correct that tomorrow morning.
Okay.
And so the moment equations are all wrong right now for for problem 3 on the homework, and so I'll correct that tomorrow.
All right. Thanks so much.
Yeah. Do you have a cat, Brett? Oh, I see. Well, I hope you guys stay warm and dry. It's cold out there. All right, Brianna, Brian, Charles, any final questions? All right, I'll see you guys Thursday. Okay. Yeah, if you're running into problems with the homework, just you can send me an email. Usually it's easier for me to look through your work and to kind of help you with that, because it's it's a bit easier like that. All right, see you Thursday.